So what we have is called a system of two equations with two variables, x and y. And I need to find an x and a y that satisfy both of these equations at the same time. So there are two different methods that will develop over the course of the semester for doing this. The first method that we're going to talk about today is called substitution. And the second method that we'll talk about in our last run through the course material is called elimination. Now, the good news is that both methods work all the time. So it's not like, substitution works in some cases, elimination works in other cases. It might be the case that one of them works more easily in some cases than others, but the good news is that they both always work. So whichever, if one of these two methods connects with you better than the other, then you can just hang on to that one and just use that one. I'm never going to ask you on an exam question specifically use this method or use that method. So whichever one works better for you, that should be the one to use for you. It turns out that for this particular system, elimination is a little bit easier. But today we're going to treat it as a substitution problem. So here's the idea behind how to solve a linear system of equations with substitution. The idea is to isolate one variable, either the x and the y or the y. So get either the x or the y by itself from one equation, and then simply substitute, or I'll just use the colloquialism, plug in, to the other equation. So use one equation to isolate the variable, and then plug that value into the other. That's the game plan here. So for example, I can choose either of these two equations. Let me just choose the first one. Let's take that first equation and try to get one of the variables by itself, either the x or the y. Which would you prefer? Doesn't matter, so this is up to the first person who decides.
X.
Yeah, all right. Get x alone. Okay, so from the equation x plus y equals 12, how do I get x by itself? What's my one step? Yeah, I got to get that y off of the x, which means doing what with it? Since it's being subtracted in the original equation, I'm sorry. You had it right, and then I transcribed it wrong. Yeah, like I said, that's where my head is right now. Nowhere. X plus y equals 12, so I need to subtract y from both sides. So what I find out is that from my first equation, x is equal to 12 minus y. So that's what my first equation tells me. And then here comes the step that makes this the method of substitution. I know that whatever solution exists for the intersection point of these two lines, that solution will satisfy that its x-coordinate is equal to 12 minus its y. So that means that anywhere that I see an x, I can replace it by 12 minus y. So substitution means taking the x from the other equation and replacing it by 12 minus y. So this is where the magic happens. This is what makes it the method of substitution. So that now that equation is going to look like 12 minus y plus y is equal to 5. And I screwed it up again. Minus y, not plus y. There we go. So that's the step that makes this method a method of substitution. We took the expression that we found for x, and we just replaced x in the other equation by that expression. So x became 12 minus y. And the magic of that is that now this new equation does not have any x's in it anymore. It only has a single variable y that we can solve for and get a number as our answer. How should I solve the equation 12 minus y is equal to 5? Exactly. I need to get the y by itself by first combining those like terms together. What do I get with minus y minus y? How many y's do I have there?
2.
2 of them. And they're both being subtracted. So negative 2y. Then I have my 12 from out in front. 12 minus 2y is equal to 5. Now we've simplified everything completely. It's just a matter of unwrapping the y by reversing the order of operations. Subtract 12 from both sides. That's going to give me negative 2y is equal to 5 minus 12, negative 7. And then to get the y alone, what's my last step? Divide by negative 2. Negative 7 divided by negative 2. Well, all I can really do with that is just cancel the negative signs. And I get that my y value is equal to 7/2. And sure enough, if I go and I ask a calculator what is 7 divided by 2, it is 3.5. Right? So that does jive with the value of the y-coordinate in the intersection point that the grapher is telling us about. So now we know that the y value of the intersection of these two is 7/2. But I can't stop there, because I also need to know the x value. That's the tempting thing, is you often do a lot of work to find that first value in a solution of a system, and then you forget that you also need to find the second. We're not done until we specify the value for y and the value for x. So now that I know y, how can I find a value for x?
You just, instead of putting y, you just put 3.5.
Yeah, exactly. So I'm going to use that same substitution trick. Now that I know what y is, I'm going to call it 7/2. That means that wherever I see y in my original system, I can just substitute 7/2 for it. And I can do that in either of my two equations. It doesn't matter. I'm going to choose to use the second equation for no particular reason. And so now my original second equation, which used to be x minus y is equal to 5, now becomes x minus 7/2 is equal to 5. Which also is an equation with only a single variable in it, which means we can solve for x just by unwrapping the variable, reversing the order of operations. Adding 7/2 to both sides. And so to find the value for x, we just need to add 5 plus 7/2. I'm adding fractions, so what do I need? I need a common denominator. What's a good common denominator for these two fractions? 2. The second fraction already has a 2. So to bring the first one up into those terms, I just need to multiply the denominator by 2 and the numerator by 2. And now that both of my fractions have a denominator of 2, how do I add them? Just add straight across in the numerators. So that I get x is equal to 17/2, which if we plug that into a calculator, 17 divided by 2 is in fact the same 8.5 that the grapher tool came up with as a solution for our system. So the most important thing about this process is the process, right? Not our final answer, but this process is something that's repeatable. Any system of linear equations that you have, any system of two equations with two unknowns, we can use this strategy of substitution to try and find a solution for. If one of our equations already has one of the variables isolated, then substitution is much easier. We wouldn't have to do this initial work that we did here, right? We had to do that because in our original system we didn't have one of the variables by itself. Right? So that was an initial step that we did here that we wouldn't have had to do if our system already came with it that way. Right? Which is why I noticed at the beginning that elimination is going to be a little easier for this example. But for all the examples that actually ask you to use substitution, they do so because it comes to us in a form where one of the variables is already by itself. But regardless of which way that happens, the substitution step is the important step, where we take that expression and plug it into the other equation to eliminate that variable and give me a single variable equation that I can solve using the tools that we have at our disposal to solve linear equations. Then substituting that value that we found back into either of our original two equations, we can find one more equation and solve for the other variable.